So today we're going to switch gears for a bit. We spent 3 lectures, almost 3 lectures on dynamic programming. And today we're going to sort of start another sequence of several lectures, I think about 3 lectures, where we're going to talk about actually continuous optimization problems. Okay? And specifically the sort of big subject that we're going to talk about is linear programming. Okay? It's another very general algorithmic technique. In fact, later in the course, when we talk about reductions, we'll even prove that this technique is to some extent the most general among all the techniques that we talk about this semester. Okay? So, before getting into linear programming, I want to just sort of frame the problem, what it means to talk about optimization problems, and then sort of talk about it. Okay? So that's the plan for today. Can you hear me? I feel myself a little low. It's fine. Okay, it's a little low, right? I mean, I'm not sure how to do that. Let me see if there's a control for volume somewhere here. There. We want to maximize x1 through xn, right? I'm going to maximize this function subject to all the constraints being satisfied, okay? So we want C1 through, so C1 says true, P here, true, and all of them say true. Okay? So only consider settings of the variables that make all constraints simultaneously happen. Okay? This is a very general form, and pretty much a very large class of optimization problems can be framed this way. It says, put down what you care about, okay, in terms of your variables, constrain them however you want, okay, and then just maximize, okay? The only thing is, and we can also go back to the last few weeks, as we cast many problems we've discussed, basically in this fashion, okay? So what's special today? What are we going to say that is new? We're actually going to focus on a particularly interesting subclass of optimization problems that are called linear programs. Okay? Before I get there, is this clear? Okay, so a variable, some number of variables, some number of constraints, a function that we care about, and subject to the constraints, we want to just maximize the function. Now, in linear programming, we're going to impose some structure on this fairly general optimization problem, and we're going to say that everything is linear, namely the function that we want to maximize is linear, and the constraints we want to maximize is linear. So let me make that clear. So in linear programming, what we want to do is we want to solve optimization problems where two things hold. One, the objective function is linear. Okay, can anybody give me an example of a linear objective function? For example, on two variables. Let's say f takes x1, x2. So what is an example of a linear function? Like x1 plus x2, or you can even put in down some scalars, right? You could write down 2x1 minus 3x2. That's a linear function, okay? Basically, you write down any of the variables with some scalars in front and you add them up, okay? Can you put a constant, yeah, sure, you can put a constant at the end, you know, plus 7. Okay, that's a linear function. Okay, so that's one constraint. We're going to put that the objective function is linear. And secondly, we're going to say every constraint is linear. Just an example. So let's see. So let's look at maybe C1 that also takes as input maybe two variables, x1 and x2. What would be an example of a linear constraint? That's another way to put it is x1 minus x2 equals 0. That's definitely a linear constraint. Look, there is a scalar, the number 1, times x1. Then see, here again we have the scalar minus 1 on the variable x2. We add them up and we say that equals 0. Okay? And you know, we could also say maybe minus 8 equals 0. You can say that it's also allowed to have a constant coefficient. Okay, so we can have linear equalities. Okay? Another constraint that we're going to be interested in and we'll be able to talk about is linear inequalities. Okay? Can somebody give me an example of a linear inequality? Yeah? Great. So x1 greater than x2. This is definitely a linear inequality. However, we will actually disallow it in this particular form. Specifically, we will want all inequalities that we consider to allow the possibility of being equal. So whenever we put down a greater than, we must also give the possibility that it's okay for them to be equal. Okay, so we can write x1 greater than x2, but we should actually write down greater than or equal. Okay? And this has to do with I'll point it out a bit later, but essentially what we want to do is to have the geometrical property that the set of feasible solutions has limit points. We'll get to it later, doesn't matter too much. But if you just say something is greater than, you can sort of get infinitely close. The two sides can get infinitely close to one another without ever actually meeting. Okay? So if you allow greater than or equal, or less than or equal, then you can say, look, there is a limit point. Okay? So it's we'll get to that in a moment. Okay? Okay, that's a linear inequality. Can somebody give me maybe just as another example, another linear inequality? How about maybe x1 is greater than or equal to 0? I mean, this will often appear. Maybe we are talking about quantities that mean something physically, and so you want to just say, you know what, each variable in its own is negative. Okay? So x1 is greater than or equal to 0. By the way, notice that equalities actually are essentially two inequalities, right? If I want to enforce x1 minus x2 minus 8 equals 0, it suffices for me to write down two inequalities. What are they? Yeah.
x1 minus x2 is less than or equal to 8, and negative x1 plus x2 is less than negative.
So the two sides of the, right, so I can just sort of write this entire thing either as I just apply greater than or equal to 0 and at most 0, right? So the intersection of these two constraints is precisely equal to 0. I guess what you said. So I just want to say that we can just talk about inequalities, because equalities are just special cases. Okay? It just says two inequalities of the two sides that holds together simultaneously. Okay? So linear programming is just basically going to solve optimization problems where the two things that we have up there, the objective function and all constraints, are linear functions. Okay? The variables are just variables. Does it make sense? Now we're going to go through an example. Okay? But is abstract definition? Good. Alright. So let's go through an example of a linear program. Okay? So say that I don't know, like there you are, and I don't know, you're selling food on the street. Okay, so it's your cart, and maybe you're selling two different types of food. Maybe say chestnuts and corn on the cob. Okay, usually they're always sold. So when you have street vendors, at least in Europe, they often sell chestnuts and corn on the cob, right? So we didn't sell chestnuts, roasted chestnuts. I don't know if you ever tried to eat raw chestnuts. They're really terrible, but if you roast them, they're really good. And then corn on the cob. Okay, and so your cart actually has a maximum capacity. Okay, say 100 units of volume. Right, and there's only so much food you can stash in it for going out and selling for a day. Okay, so you're at home, scratching your head, and you have a rough sense of what is the daily demand of each of these two items, but each unit of these two items has a certain cost and occupies a certain amount of volume. Okay? So you want to try to maximize your profit, subject to certain constraints. Okay, we can try to tabulate these constraints and then sort of encode them using linear constraints. So one can write down, say, a table that says, okay, so the chestnuts each time I sell them, each package that I sell will give me, say, $2. Okay? And the corn will profit me, say, $4. Okay. But we also have some constraints. Maybe we know that corn is a lot more popular, right? So we have some daily demand that maybe it has been estimated overselling over the past few weeks, and maybe the chestnuts it's going to be 50 boxes a day and 80 boxes of corn. Okay? And obviously, right, if you bring fewer boxes, what does it mean? It means that if you bring more than 50 boxes of chestnuts, you probably won't be able to sell all of them. If you bring fewer boxes than 50, it means that likely you'll be able to sell all of them, and little for the corn. But you have a limited amount of space, right? So you need to, and these two things actually yield you different profits. So which ratio you put inside here is an optimization problem. I could, by the way, I could also add another column to talk about, for instance, maybe a box of chestnuts and a corn on the cob occupies different amount of volume. Let's just say that for now they occupy the same amount of space, and each of them, when I put them in the box, occupies 1 unit of volume. Okay, just for simplicity right now. So that's what we have. And so you're asking yourself, what is the max profit in a day? Okay, so that's kind of the setup. What I want to try to do right now is to kind of distill from this caricature setup a linear program that represents what you're interested in. Okay? So let's try to do that. That's the setup. It's a pretty simple setup. Just a good start. So, where do you think the objective function is? What is it about? Profit, right? So that's what I care about maximizing. Okay? So F is going to be the profit. Let's try to write it down. So now at some point I need to introduce variables. For example, how many variables should I have? Yeah, that's like a reasonable guess, right? It's not always obvious what the variables should be, but here it's probably clear, right? So 2 variables, let's call them x1 and x2. And x1 will represent the number of chestnut boxes that I'll put into my cart at the beginning of the day. And the other one will represent the number of corn again, boxes or all that are put into the cart at the beginning of the day, right? So those are kind of my decisions. And what is my profit as a function of these 2 variables? So, great. 2x1 plus 4x2. Is it linear? Yeah. Look, why is linear programming relevant many times? Because many things are linear. Profit is, for example, one of them in this particular case. Okay? Alright, so we are interested in maximizing this expression. Now, of course, we could just say set x1 to be infinity, and maybe even x2 to be infinity, or twice the infinity, right? And then we have 2 times the infinity profit, right? So that's in principle fine, but actually we have some constraints, right? We have a finite size cart. Okay, we have to stash everything we bring for the day there. Okay? So now let's talk about the constraints. So what are some constraints? Yeah, x1 plus x2 is at most 100. Why? Well, because if I choose to pick x1 boxes of chestnuts and x2 boxes of corn, and I put them inside the cart, and each of them occupies 1 unit of volume, we have assumed that each of them occupies 1 unit of volume, then I can put at most 100. Okay? We should verify that this is a linear constraint. It is. Okay, good. What are other doesn't matter. Yeah.
X1 is at most 50.
X1 is at most 50, right? I know at the beginning of the day that I'm not going to be able to sell more than 50 boxes of chestnuts, so there's no point for me to stash more than 50 into my cart. Okay? There it is, also linear constraint. How about another one?
X1 is greater than 0.
Great. So don't forget that we're selling things that, the actual objects, right? So I cannot sell you like a negative amount of chestnut boxes, right? So I should make sure that I encode into my problem x1 greater than equal to 0, because it's not like the problem knows that I'm talking about chestnut boxes. It just knows about x1, right? So I have to tell it, look, please don't ever set the variable x1 to be negative, because it will not make sense to me. Okay? Okay, and then we have the other constraints, the analogous constraints for x2. x2 should be at most 80, and also non-negative. Okay? So how many variables we have? We have 2. Okay? How many constraints do we have? 5, right? 1, 2, 3, 4, 5. Okay? 5. Okay, so we have written a linear program. Okay? So that particular problem up there, we were able to kind of encode into an instance of a linear programming problem. The big question is, after you've written it, how do you solve it, right? We're interested in getting the answer, right? So we want to know, among all the choices of x1 and x2 that satisfy these the constraints, which one is best. Okay? Now, because here we have a small number of variables and a small number of constraints, we can actually try to draw this, okay? Because each choice of x1 and x2, we can think about it as a point on the plane. Okay, we can draw. So, right now we're actually going to draw kind of things about this linear program, the reason about the solution, and then we'll try to sort of learn from that and think about what we can do in the general case. Okay? So, we're going to stick again with this example, and we're going to draw. Okay? So, we have two variables, and as I said, we can think about the two variables as representing points in the real plane. Okay, so that's kind of my choice of x1, and that's my choice of x2. Now, what should I be drawing in this plane? What's interesting to draw? The constraints. Okay, what are constraints going to be in this picture?
There are linear subject boundary lines.
Right, they're half spaces, right? So each of these constraints slices the plane according to some line, and we're interested in it slices the plane into two halves, and we're interested in one half of it, right? For example, let's look at a very simple one. x1 greater than or equal to 0 says, take this line, and please stay above it. Right? It just says consider this half plane. Okay? Discard everything down here because it makes no sense. Oops, sorry. That was x1 greater than or equal to 0 means this line here. It says, please consider only x1 to be non-negative. There's no point to consider x1 that is negative. This x2 here says, please stay above this one. So this is already saying that the obvious thing, which is we should consider only the top right portent of the real plane, right? Okay, then we also, so that's two constraints. We have 5, right? So what about this one here? This is also a line, right? And we can draw it, right? How does it look, the line? Right? It kind of slices this way, right? It meets the x-axis at the point 100, 0, right? Because it is on this line. We set this equal. And it meets the y-axis at 0, 100. So that constraint is saying, take this almost line, right? And look inside here. Right? Each constraint tells us to discard some number of solutions. We need to keep taking the intersection because we have to satisfy all constraints. This line, how does it look? It's a vertical line, right? It says, look at, say, 50 here. So the point, look at 50, 0, right? And this is the line that corresponds to x1 equals 50. That's right, x1 equals 50. And that constraint says, look on this side, right? So this region that previously was feasible, now it's not feasible anymore because we discarded it. And this last constraint, x2 is at most 80. It says, up here, draw a line, a horizontal one, x2 equals 80, and consider things below it. Okay? Are we done with constraints? Yeah, we're done, right? We draw 5 lines. 1, 2, 3, 4, 5. All of them have been drawn. And what I'm interested in is the intersection of all the half spaces induced by each of the constraints. And what is it? Well, it's this region here. Right? It's this almost rectangle, right? Maybe let me draw it a bit. These are all the solutions that we're allowed to consider for the purpose of maximizing our objective function. And the way to put it is, these are any point here, it's a choice of what to put in the cart that makes sense for the problem. Okay? So I haven't done anything so hard so far. I'm just going slow because in a moment it's going to get more harder. Okay, so we understand the set of feasible solutions. How do we think of the objective function now? What is the objective function, so relative to this picture? Geometrically, how can I think of the objective function? Yeah.
It's like the maximum value of a regression function in that domain.
Yeah, it's definitely the maximum inside here, but there's a very explicit geometrical explanation. Yeah. It's a plane coming off of the board. So far I want to stay inside the board actually. I mean everything is. I can't think about it as you can think about it as some. You could try to plot in this direction, right? The value, right? And you would get some sort of landscape, right? Some 3D landscape that sort of represents at each point kind of what's happening. In principle, it could look really weird, right? It could be like there's some bumps here, right? But actually, because the thing is linear, it will actually have a very clear structure. That's why we can actually don't really have to think about things coming out of the board and directly talk about them inside the board. Yeah, up there.
So the maximum velocity will consider or one of the
I'm trying to get something, it is, but I'm trying to get a little bit something crisper for, yeah? Excuse me? Area. I would like to say that the objective function is a direction, right? So a linear function says, please go in a particular, very specific direction. So let's try to I want to try to convince you of that. So let's look at this particular linear objective function. We can draw so-called contour lines. Those are lines on which the objective function is constant. That's kind of similar to when you look at a topographic map and you see contour lines that give you the altitude. Right? If everyone hiking, for example, right? You get a topographic map where altitudes are shown using contour lines. Like there's a line that says this is 100 meters. The next line is going to be some other contour line, it's 150. We could try to draw the contour lines of this function in here. And those contour lines will actually have a very specific structure that will say that we should think about this one as a direction. So, for example, let's draw the contour line for this one equals, let's say, 4. Okay? So let's look at the contour line where 2x1 plus 4x2 equals 4. This is not just a line, it's literally a line, right? That's a line. So how do we draw it? Well, it suffices to have 2 points and then we just draw through the line. So here an example of 2 points that are on this line. One would be, say, 0 and 1. Right? This is definitely on this line, right? Because if I put in 0 here and 1 here, I get 4. Right? And another point in this line is 2, 0. Right? I can just put 2 here and then 0 here, I'll get 4. These are 2 points on the line, they're fully determined. So where are they here? Well, 2, 0 is somewhere here. That's 2, 0, right? And 1, 0, or 0, 1, sorry. 0, 1 is somewhere here. So this is basically saying that there is a line this way. Now, as I change this parameter, let's say that I double it, I make it 8. How will these other contour lines look like? There's like shifts, right? So once I've drawn one contour line, all other contour lines can just look the same. They have just a different value. So it's not like on a mountain topographic map where just the contour lines could be whatever. Because this is a linear function, the contour lines just go in a specific direction. So actually I can characterize this direction as a vector, any vector, that is orthogonal to all of these lines. That's like the direction relative to which I want to travel in order to maximize my function, right? Because as I increase this one, which is what I want to increase, my lines sort of move this way, all in the same direction. It doesn't matter where I am on the line, it's all the same. All that matters is moving that way, right? And I think my arrow has to be a little bit pointing outwards. There we go, something like that. Once you have this, visually, it is clear how you solve the problem. One way to think about it is to just take the drawing, you rotate it until this line is pointing downwards, and you drop, I don't know, like a ball inside it, and where the ball stops, that's the maximum. Or you can just keep moving this direction until you can't, right? And it should be this point here if I've drawn things correctly. We'll check it in a moment. Okay? Basically, you want to push in that direction until you can't anymore. Okay? Is it clear what I'm saying? What I really wanted to say was contour lines are not arbitrary. They are lines, like straight lines. And you can think about your objective function as a vector orthogonal to all lines that tells you in which direction you should go. Okay? In this case, the direction it says, goes roughly up, right? And we can check, as we'll check in a moment, that this point is further out relative to this direction than this point is, because there will be some contour line that passes here, and this point is further relatively. Okay? Okay. So what I want to do now is I want to try to make some of the geometrical properties of these type of things more formal, so that we can try to think about how to solve things that we can't draw, right? This time we drew it, and you could literally solve this by hand, right? You just make a better picture, right? And then you figure out what is the furthest point in the direction that you want to go. Okay, that's how you solve it, okay? By the way, probably something like this you might have seen in private courses or maybe even high school. Like this two-dimensional linear programs, sometimes they're covered in high school. I don't know whether they're called linear programs or not, but it's just optimization. Questions about this before we move away? We have found a solution for this one, okay? Alright, so let's put the program up there. The linear program up there. And now let's take take a step back and I want to try to argue some properties about the set of feasible solutions so that once we learn these properties, we can formulate some strategy to tackle the problem in general. So, let's call them geometrical observation. So, the first thing we're going to do is we're going to argue that the set of feasible solutions for any EM program is convex. We're going to use this very strongly. So, does anybody remember what does convex mean? But what is not convex? Okay, here's a better example. A banana is not convex, right? Why? So that's a banana, right? It's not convex because if you draw a segment between any 2 points, it might exit the shape. So if I take, for example, a point here and a point here, and I draw a line through them, then it goes outside the banana, right? So that's what not being convex. So that's a violation of convexity. An example of something that is convex would be an egg. It's an egg, right? And between any 2 points that I draw, I can draw a line between them, and the line will be wholly contained inside the shape. Okay? So typically you've seen convex before on when we're doing real analysis, right? When you look at sort of things that look like this, right? But in general, convexity means that you take some object, it has an interior, right? And you're allowed to draw lines between any 2 points, and if all these lines are still inside, that's convex. Okay, so is it clear the difference between a banana and an egg? Okay, so now I want to write down formally what that means, because we're going to actually prove it. It's not going to be hard at all. So it means that if x and y are, let's say, in, let's say f, the set of feasible solutions, then how can I break down any point z on between x and y? What's one good way to write point z between x and y? I want some parameterized way to write z. Yeah?
Alpha x
Yeah, alpha x.
plus 1 minus alpha y.
Excellent. So this is a general point on the segment between x and y, right? And then, so then for every alpha between 0 and 1, the point z, which is somewhere between x and y on a line, is also an f. So this is the formal definition of what convex means. Okay? And we want to prove that if I have any 2 feasible points, okay, then I take this type of sort of linear combination where alpha is between 0 and 1, so which means I go somewhere between them, I still have a physical point. Okay? X and y are physical, then any z between them is also physical. Okay? This is what arguing that the set of feasible solutions is convex means. Okay? And so let's maybe try out this definition for one constraint here, right? So one way to prove this would be to just say that if x and y satisfy some constraint, then so does z. Clearly, if x and y satisfy every constraint, then so would z as well, right? So let's just focus on one constraint. And let's start with an example. Let's say x1 plus x2 is at most 100, right? So let's just look at the example. Let's say that we have x1 plus x2 is at most 100. That's my x. and I know that they satisfy. So then I also have y. Okay, so y is also feasible. It satisfies this constraint, right? Now I'm interested in whether alpha 1, so alpha x1 plus 1 minus alpha y1, so that's kind of the z1, right? Plus alpha x2 plus 1 minus alpha y2, that's my so z2, is at most 100. Right? Do we agree that that's what I want to prove? Right? I'm saying, give me 2 points that satisfy a certain constraint. I want to check whether z, whose z1 looks like this and z2 looks like that, also satisfies that same constraint. Okay? Do you agree that this is what we want to prove? Wait. Is it the case that this holds and this holds, then this holds? How could I derive this one from the other two? Idiot?
You multiply the first line by alpha, the second by like 1 minus alpha.
Right. So say that I multiply this entire thing by alpha. What does it mean? Clearly, if x1 plus x2 is at most 100, it is also true that alpha times x1 plus x2 is less than or equal to alpha plus 100 times 100. Notice that alpha is between 0 and 1, it's not negative, so it doesn't flip the sign of the inequality. Right? There's something you have to pay attention when you multiply things in inequalities. If you take an inequality, you can multiply both sides by the same non-negative number. Right? I can also multiply this one by 1 minus alpha. I'm going to add them up, and I get precisely this thing. Okay? Alright, so this is just an example, but in general, let me do it in the other word up here. So in general, we have some linear constraint, right? That doesn't have to look like that. What is the general form for a linear constraint? Give me some linear program, right? I'm looking at any of these constraints. It is a linear constraint because it's a linear program. So how would it look like? Syntactically. Excuse me? That would be the entire thing. I'm just looking at one constraint. It's something simpler than a matrix. Yeah?
Scalar, let's see,
Just arbitrary scalar.
is less than scalar.
Excuse me?
X dot with the dot product is basically a sum of
Yeah, it's a dot product, right? So, general linear constraint, it says, take some arbitrary scalars A and take the dot product with X, right? That's, I don't know how you write the dot product. Dot? Okay. Alright, that's a dot. That's a dot product. So take a vector of, these are not variables, these are constants, okay? Constants like 1 and 1 or 2 and 4, okay? Take a dot product with X, okay, get something, right? And this should be at most B. In general, this is definitely a general linear constraint, right? So we have that, and we also have the same thing for Y, because we're saying that both X and Y are feasible. In particular, they both satisfy this constraint, which is some arbitrary constraint inside a linear program. And then I can just do the same thing as up there, right? You can just say that, look, I I can multiply this thing by alpha, right? So maybe from here I can just say multiply by alpha both sides. So alpha times whatever is inside here, the most alpha beta, alpha b. Then the alpha, I can move it inside, right? I can just say this is the same as A dot product alpha x. Right? What is alpha x? It's just the vector x where I'm sort of multiplying each coordinate by alpha. Right? So this entire thing here, I can multiply it by 1 minus alpha. Right? I'll get A dot product y at most 1 minus alpha b. Right? And I can again move the 1 minus alpha inside. A dot product 1 minus alpha y at most 1 minus alpha b. Right? And now if I take these two guys and I add them up together, I will get that A dot product z is at most b. Right? Because I sum this one with this one. Now alpha b plus 1 minus alpha b is just b. Right? Here I can collect A, and what's left inside is alpha x plus 1 minus alpha y. That's z. Okay? So what we're saying is that if x and y satisfy the particular constraint, then so does z. And that's true for any constraint. So that if x and y were feasible, so is z. This just shows that the set of feasible solutions is a complex set. Okay? Do we agree with that? Alright, see people shaking their head. That's good. Okay. Wait, so what? Wait, fine, it's complex. Well, it turns out that thinking about it as a complex set is an important insight to try to come up with algorithms. Okay, because so far, by the way, what is our best algorithm so far in general? I mean, we haven't really sort of talked about it, but without saying more, if all I told you was here's a linear program, please solve it, in the general case, what would you do? Try all the points, right? It's a pretty lousy solution with an infinite number of points, right? Many times, at least we have a bad solution that is finite, right? But here, we're scraping at least for something finite, right? You cannot try all the points. I claim that now convexity is going to take us at least to an algorithm that runs in a finite amount of time. Okay? This is what I explain now. I want to explain next. Right. Are there questions about this before we move there? Okay? But wait, the example doesn't count, right? We just eyeballed it, right? So, but in general, you may have to try everything inside the physics. Yeah. Can you ask your question again? So here, this is Z1, and this is Z2. So we're saying that Z1 plus Z2 is at most 100. Right? So we wanted to conclude from that assuming that x1 plus x2 is at most 100, and y1 plus y2 is at most 100, we're going to say that anything between them, Z1 plus Z2, is at most 100. Good question. Alright, so let's talk about how convexity can help us come up with a finite algorithm. It will not be a good time, but it will be at least finite for linear programming. Okay? Okay, so given an instance of linear programming, somebody gives me like an objective function and a bunch of constraints. So there are various things that can happen, okay? So one, it could be that there are no solutions, okay? Right, it could be. Okay? Maybe you were asking that, I don't know, one of the constraints says x1 should be at least 1 and the other one should say that x1 is no more than 0. That clearly doesn't leave any, there's no physical solution. Right? So that could be an option. Another option is that it could be unbounded. What does it mean? It means that you can keep maximizing and there's no half plane that will stop you. Okay, so an example would be to say maximize, I don't know, x1 plus x2 subject to x1 and x2 are non-negative. You know, clearly I cannot find maximum value, which just keeps going up, right? The third case, which is the one of interest, I just wanted to sort of, I wanted to kind of rule out these sort of uninteresting cases, is that the solution or rather, the best solution is what? So I want to apply convexity now. If it is, there are solutions to be talked about, and it is not the case that you can just keep increasing your objective function unboundedly, then what can I say about an optimal solution using convexity? Where could it be? Could it be that I have a solution that is somewhere in the middle? No, right? Because you could just keep moving, right, in the direction that you should be moving, right? So the solution should be somewhere, right, on the boundary. What type of boundary should it be on? Yeah, I'm going to say that. If you look at the vertices, you will always find an optimal solution among them. Okay, so the solution is among the vertices. Okay. Now, why would that be? Well, say, in principle, we have some complex sort of a set of half spaces in high dimensions, right? And first, we should realize that there's no point to be in the interior, right? In the interior, you just keep moving in the direction you should be going. So that's definitely no good, right? Now suppose that I am somewhere that is not a vertex, it's on the boundary, right? Say that I'm over there on some face. Now this is a flat face, right? Because it's imposed by a half space, right? Two things happen. Either the contour lines for my objective function really completely line up with this face, at which point I can, without a lot of generality, just move to one of the vertices. Right? Say that I'm on a face, but not on a vertex. Right? Either I'm in a situation where what I'm trying to, the contour lines for the objective function are exactly parallel to my face, in which case it causes no harm to just scooch over a bit, right, and end up on a vertex. So we can just kind of, if we were here, we can say, okay, fine, there's many optimal solutions, just pick one on a vertex, so that this claim definitely holds, right? In another situation, if instead I'm saying, well, suppose you were here, but when your contour lines can look like this, I say, well, there's no point to stay here. I'll just keep traveling this direction, and I actually improve my objective function, right, going that way. So either way, I can always move to a vertex. Okay? It doesn't mean that you can move to any vertex. It just means that there is always some vertex that will maximize your objective function. Okay? So from an algorithmic perspective, there is no point for me to care about anything other than vertices. Okay? Does it make sense? through me, it must be that the rest of the body is on the other side, because it's convex. Okay, this is why I know that this maximum must be a global maximum, right? So the analogy here is that if I'm doing some general optimization problem, right, say, and then I'm sort of traveling up, right, and say, okay, so locally here, I can only go down, so I better stop here, right? But this is actually a local maximum, it's not really the maximum. But it is not a convex curve. In a convex curve that looks like this, once I find the maximum, it must be the global maximum. Similarly here, because I have a convex body, and I find a corner, and if I go left, it goes lower down, and go right, it goes lower down, it's like, I really should stay put. Okay? Because the body is convex, it sits all on this side, I know that I'm at the best answer. It cannot be that the body has an arm that kind of goes out from this side and does better, right? That would not be convex, right? Okay, so convexity tells us this kind of sort of trichotomy, right? It says either no solutions or, there is kind of still no solutions, there's too many, right? You can keep going to infinity. Or, like, you must look among the vertices. Okay? Question? Excuse me? It will intersect. Vertex is an intersection. I said there are contour lines everywhere, right? I mean, it's a continuum, a spectrum, right? So I drew only 6 contour lines, but there's an infinite number of contour lines, for every through every point there is a contour line, right? Okay, so now I claim that this observation actually gives us an algorithm that will halt in a finite amount of time with the optimal solution. Okay? What is the algorithm? Any suggestions? So at high level, what should the algorithm do? Forget how exactly you do it. Yeah. Yeah, how many vertices can there be, right? So we have n variables, we have n constraints, okay? There's really going to be, now we're going to compute how many as an upper bound. There's only going to be finitely many vertices, right? So just somehow figure out all of them, okay? And just pick the best. Convexity will say that even though you've looked at finitely many points, actually the best among those finitely many will actually beat all the other infinite points instead in the feasible set of solutions, okay? Kind of the proposal is kind of list all vertices and pick the best. Okay? So, what is a bound on the number of vertices? The vertices as an upper bound, okay? Yeah? And choose 2 for 2 variables, yes. In general, I have n, so first let's kind of understand why. So say that we have 2 variables, and we have n constraints in general. Here we have 5, right? But a vertex would be the intersection of 2 constraints, right? In this particular case, so you have a line, half space here, right? Here, for example, that's a vertex, this intersection of this constraint and that constraint. Okay? So does it mean that every intersection of 2 constraints is feasible? No. For example, this one is an intersection, but outside the feasible one. It's okay, right? So whenever we examine this one, we can recognize that it violates some other constraint and we discard it. Okay, but we can still talk about an upper bound on the number of all possible vertices. Here, the upper bound would have been 5 choose 2, which is 5 times 4, right? 5 times 4. which is 20, divided by 2, 10, right? But we have only 1, 2, 3, 4, 5 actual vertices we care about. That's okay, we said that 5 is at most 10. Okay, right? In general, if we have n variables and m constraints, what is an upper bound? Not the exact number, an upper bound, the number of vertices of the feasible region. Yeah? That is very optimistic. It will be a lot more than that. N choose 2 is still very optimistic. It's a lot more than that. M choose n, right? Because what's happening is that we are picking a system of linear equations in n variables. It becomes completely defined when you have n constraints, right? Because think about it. When you take two of these two things, what are you doing? You say pick, say this one and that one. We want that system of linear equations to have one solution, the vertex, right? If we have some number of linear equations in two variables, we need two of them to constrain the system to get one solution, right? In general, if I have n variables, I'm going to need n independent equations to constrain it to one point, a vertex. Okay? So, here, in general, it's most m choose n. It says, pick any n out of the m constraints and make a point out of it. Some of them will be feasible, some of them will be infeasible. It's okay. Anyways, this will be an upper bound. So this is saying that we only need to list at most m choose n vertices. Roughly, what is the order of this expression? Yeah, it's roughly on the order m to the n. So it clearly doesn't look polynomial, right? So we should think about both m and n as polynomial, right? But yeah, it's fine. This is also less than infinity, right? So for sure. So this gives us a sort of algorithm that runs behind. Okay? Yeah, it's a very quick proof, right? So we should not underestimate. So that's fine. I want to maybe make this a little bit more precise, and it turns out that something not very far from this ends up being very, very good in practice, despite sort of having horrible upper bounds. Though, since we thought very hard, it'll take 2 minutes just to say something stupid, and then we'll say something smart again in 2 minutes. So let's talk about maybe 2 words today. So we talked a lot about this C versus CH, right? We also talked about the quantization, right? L versus GL and N versus GM, right? Today I want to talk about another way that the C changes, okay? So here's an example. So, does anybody know this word? No, it's good to be ready, it's fine. So this is scolio, right? So this is using what we learned last time, here, right? And in front, what's interesting is that, okay, S followed by C, and O, that sounds reasonable, scolio, right? But it means rock. Specifically a rock that is part of a reef. However, sometimes you want to create the sound sh, okay? So then you sneak in an I, and you can write, for example, a shock roll. Okay? So this I is kind of the opposite of H. H creates a hard C, and this I creates a soft C. Okay? So Shopko actually means an idiot. So what is that? So the only difference here is that there is the I that makes it like that. Let me give you another example, maybe scintilla, where this I is going to create this sh sound. What does this word mean? Spark. Like that, you know, when you heat metal with metal, or when so spark. Okay, so today it was about how I plays with C, as opposed to how H plays with C. Okay, so much for that. Now when we sort of relax a bit, let's talk about what we're going to do about this final size algorithm. Okay. Now there is there's a lot of freedom in this algorithm, right? It could be that listing the vertices in a certain order versus another order is better. Okay? Now, maybe, like think about it, right? So there's all these vertices, right? And these vertices are not just random, right? They have relations to one another. So for example, if you go, let's say that the direction is this one, okay? That's kind of the direction in which we want to go. And for whatever reason, you start listing vertices here. Say that your first step says, I'm going to consider this one next. I consider this one, I say, oh, it sucks, it has very small value. Let's try some other one. This one has higher value, it's a better choice. Which direction should I go next? Should I be jumping around randomly? Should I be following some strategy? Yeah, that's kind of so you can keep track of which constraints are kind of fully satisfied, and maybe you say, well, really, I met this constraint, but then when you actually leave a vertex, you have to relax some constraints, right? So, intuitively, what you want to try to do is gradient ascent on the boundary, right? A bad strategy would be to just pick at random, because that clearly has no logic, okay? And there are too many vertices. You could be, there's only one good one potentially, right? And you're just jumping around across all the other ones. Turns out that very good strategy in practice is to basically keep moving to neighbors of yourself that improve the objective function, right? Now, in two variables, it's not very interesting because you have two neighbors. You came from one, you must go to the other, right? So you don't really have a very sort of rich choice. But in higher dimensions, okay, you come from some neighbor. Your next neighbor could be many things, right? Just pick the one, anything that improves, okay? And just continue improving until you get stuck, okay? This algorithm actually has a name. Let me dedicate full work for it. Something called the simplex algorithm or method. By the way, it's called simplex not because it's simple, but because simplices are these high-dimensional geometric public objects, right? But it is a simple algorithm. So the simplex algorithm says just start at any sort of feasible vertex. Then move to any, really doesn't matter, any adjacent vertex. That improves the objective function. Okay? If there is no way to improve, namely, you are at a point where none of your neighbors is such that the objective function is better, then you hold and you output wherever you want. Okay? So this is not fully specified still, right? Because maybe they're among the various neighbors that improve, which one should you pick? But I'm just saying that it's a little bit more concrete than this one, because this one could have been just pick them really in arbitrary order, not according to neighbor relations. Okay? Now, in practice, these neighbor relations are actually moves that you can efficiently do. Because a vertex just says you have n constraints that are fully satisfied, right? They're kind of equalities. You can relax one of them, right? And just make equality some other one. That would be a move to some neighbor, right? And you can consider, where is it? But out of the n constraints, n were satisfied as equality, you can just drop one of them. You could consider any of the other n minus 1 as possible for making another vertex, and that's how you can make your choices. Now, this algorithm, which is very old from I think the 40s, is very notable, because it works very well in practice. In the sense that if you code it up and you give it a linear program, it will find very fast optimal solutions. Okay? But generally it's not polynomial time. Generally it's not efficient. So essentially, for many reasonable choices for how you pick your neighbor, one can most of the time come up with counterexamples where it takes an exponential number of moves from vertex to vertex to vertex until you reach the actual optimum. Okay? Yet this algorithm is very useful in practice because it just works on sort of non-concocted, non-versatile instances of linear programming. Okay? And again, it's a family of algorithms because right now I'm just saying any adjacent vertex, but really you could sort of make this more precise with different sort of next step strategies. Now, does it mean that linear programming is not efficiently solvable? No. There are other algorithms that are sort of beyond the scope of this class that were discovered actually much later, I think in the late 60s, early 70s, that showed that actually one can solve linear programming in polynomial time, but they're just sort of beyond the scope of this class. For example, one such algorithm is called the ellipsoid method. Okay? Rather than jumping between vertices, essentially what you're doing is you're taking something that encloses the physical space and you keep restricting it until you understand the physical space better. So let me just say, fact without proof, that you should assume for the rest of the course, because it will be used, you can use it in exams, homeworks, whatnot, that any linear program can be solved in poly n time. Okay, so it says polynomial number of variables and number of constraints. Just kind of what we want to do, right? Question?
So you say when we take back the group and say reduce it down to
Yes, this is exactly how we're going to be using linear programming for the rest of this course, right? So we're not actually going to unpack what this algorithm is. We're just going to take as a fact that any linear program can be solved. And then, how do you work with linear programming? Well, you can take whatever programming problem you're trying to solve, and you try to reduce it to a linear programming instance. right? Of polynomial size, of course, right? Because if you, in your reduction, you write an exponential number of variables, that's not very good, right? The algorithm will be efficient relative to that, but you should be picking not too many variables, not too many constraints, right? This is analogous to what we did with the cart, right? The cart was not in principle a question about linear programming, but we reduced it to a question about linear programming. And what we'll see, for example, next time, is we'll start with a question that apparently has nothing to do with linear programs. It will be about flows in graphs. Okay? And we'll see how to solve that question by just casting it as a linear programming instance.